There is no need to dwell once again on the substantiation of the importance of the problem of the safety of nuclear reactors. One of the promising directions for improving the safety of reactors is the creation of passive emergency protection devices (PEPD) for reactors. With their input, the reactor acquires additional negative reactivity feedback, which is triggered when the main operating parameters temperature, coolant flow rate, power go beyond the maximum permissible values. Based on the use of such devices, it becomes possible to create nuclear reactors that are internally resistant to hardware failures and personnel errors. PEPD also manages beyond design basis accident, i.e., takes actions aimed at preventing the development of a design basis accident into a beyond design basis accident and at eliminating the consequences of a beyond design basis accident. One of the determining factors for the destruction of fuel elements in pressurized water reactors is the crisis of heat transfer during boiling, which leads to a sharp increase in the temperature of the fuel cladding, its melting, and the release of the fuel composition into the coolant. Conventional designs of direct-acting emergency protection devices did not take into account this mechanism, and therefore practically lost their effectiveness due to their inertia. Therefore, the most rational physical effect, on the basis of which the work of emergency protection of direct action should be based, is the very crisis of heat transfer, which has a pronounced threshold. At the same time, the main problem is solved, which did not allow earlier to consider the PEPD as equivalent to currently operating active systems, namely, it provides a speed that exceeds the speed of any suppressed by this tool emergency processes or their combination, leading to exceeding the established safety limits. For example, a calculated evaluation of the operation of one of the options for an emergency protection device in relation to the VVER100 a reactor showed that in an emergency during a jet accident, the response time is sufficient to prevent a dangerous increase in temperature. In the reactor, all links are given below. Analysis of the safety system using the phenomenon of heat transfer crisis based on a set of 26 criteria, considered as a tool for a rapid expert assessment of the safety of developed, operating, or modernized installations in order to analyze, compare from prototypes and options with each other, identify bottlenecks and eliminate them. The conducted criterion analysis allows us to speak about the high level of perfection of the PEPD based on the use of the phenomenon of heat transfer crisis, and, consequently, about the prospects for the development of devices of this type. However, passive emergency protection devices can be used not only for power reactors, but also for research reactors for various purposes. For example, consider a vessel-type research reactor with a neutron reflector placed in the pool. You can get acquainted with the design of this reactor in detail at the link below. The presence of an intermediate circuit operating on the principle of a heat sink pipe eliminates the risk of radioactive coolant leaks in the environment. The passive operation of this circuit provides high efficiency of heat transfer with a simple design and the absence of mechanical moving parts, which determines the reliability of the system. Air cooling of the reactor plant using a chimney eliminates the problem of water treatment of cooling towers to prevent the formation of salt deposits on heat exchange tubes and the surface of sprinklers in cooling towers. The location of the reactor vessel in the pool makes it possible to abandon expensive and complex emergency heat removal systems from the core.
The results of calculations of the reactor according to the model in RELAP 5 for a core of 30 fuel assemblies of the WWR0 type, consisting of 24 8-fuel assemblies and 6 5-fuel assemblies with CPS operating elements placed in them, showed the efficiency of the proposed cooling system and the achievability of a high level of thermal reactor power 50 megawatts, which corresponds to the neutron flux density in the central moderating cavity above 2 × 10 to the power of 15 per centimeter square per second. The safety of this reactor can be improved if one of the CPS elements is replaced with a passive emergency protection device. This device has a minimum margin before the heat transfer crisis and will work before critical conditions occur on the plate fuel elements. Upon reaching critical parameters for pressure, power or speed of the coolant, the device will operate due to a heat transfer crisis on it. This heat transfer crisis is caused by artificially degraded heat removal conditions on the wall holding a fusible fuel element in the form of a plug separating the neutron absorber from the core. The core consists of an aluminum matrix with the inclusion of particles of uranium dioxide. Therefore, during a heat transfer crisis, it collapses very quickly. When the plug breaks, a liquid containing a neutron absorber, for example, boron, is injected into the reactor core. Before the destruction of the plug, the neutron-absorbing liquid is in the tank under gas pressure, so the injection occurs at a high speed. Injection of the neutron absorber leads to the transfer of the reactor to a subcritical state and prevents the destruction of the core. To bring the reactor to power, it is necessary to unload the spent passive emergency protection device from the reactor and replace it with a new one. Despite certain difficulties in handling this device during overload, it is not subject to human errors or errors in the CPS control circuits.